I want to talk about stuff I've been doing very recently that was stimulated by a paper just a couple months ago by Hans Werner Hammer and by Dan Son. I understand that Dan Son actually gave a talk perhaps on this subject not too long ago. And so some of this will be a repeat of what you might have heard from him. But I've been working in collaboration with Hans Hammer, who's at University of Darmstadt. And I'm very grateful for research support from the US Department of Energy. So when I was in grad school, there was a standard phrase that you heard often that was an answer to the question, what is an elementary particle? And the slogan was that an elementary particle is an irreducible representation of the Poincare group. And as a consequence, it is characterized by a mass and by a spin. The Poincare group, as you probably know, includes 4 space-time translations and 3 rotations and 3 Lorentz boosts for a total of 10 dimensions. The standard model of particle physics is, of course, it has elementary particles. There's 17 of them. The spin 0 Higgs boson. There's 6 quarks and 6 leptons with spin 1/2. There's 4 gauge bosons with spin 1. And but many people are convinced that there must be something beyond the standard model, maybe more elementary particles, maybe new interactions. And one popular possibility is that there's a hidden sector in which the particles have no standard model interactions. Now, back in 2007, Howard Georgi wrote a paper called Unparticles Physics, in which he suggests that the hidden sector could be a scale invariant theory with conformal symmetry. And if so, it would not consist of particles similar to those that we see. It would consist of some other kind of stuff that might be more like a fluid than particles, but he called it unparticles. So what is an unparticle? Well, it's an irreducible representation of the conformal group, and it's characterized by a scaling dimension, a single number. Now, the conformal group is the smallest group that extends the Poincare group by having a scale transformation. So along with the symmetries of the Poincare group, you have to add a scale transformation, but then to make a group, you have to also add 4 space-time inversions. The scale transformations are singular at infinity, and these 4 space-time inversions move the singular point to everywhere else in the space-time. So it's a group with a total of 15 dimensions. And well, if you have a hidden sector, you cannot see the particles, you cannot see the stuff that it produces directly, but you can see it indirectly. For example, you can have a reaction in which a quark and an antiquark produce a Z boson, and it recoils against the unparticle stuff. And the energy distribution of the unparticles would be revealed by the momentum distribution of the recoiling Z boson. The invariant mass distribution of the unparticles will have a power law behavior with a power determined by the scaling dimension. And the CMS collaboration has written a few papers in which they have set limits on the effective cutoff scale as a function of scaling dimension if the extension of standard model consists of unparticles. Now, whoops. Okay, I'm going to turn now to non-relativistic effective field theories. And such an effective theory can have a Galilean symmetry if the mass is conserved in every reaction. Now, this requirement of conserving the mass, that's very accurately satisfied in atomic physics. It can be satisfied in nuclear physics as long as the only particles involved are nuclei and nucleons, protons and neutrons. In particle physics, it's really unusual to have a Galilean symmetry, although there is a case where this does occur that I'll come to later. The Galilean group includes 4 space-time translations, 3 rotations, 3 Galilean boosts, that is the kind of boost that you would have expected to be a symmetry of nature before Einstein came along, and also 1 phase transformation for a total of 11 dimensions. And this additional phase symmetry is what guarantees mass conservation. So if you ask, what is a Galilean particle? Well, it's an irreducible representation of the Galilean group, and it'll be characterized by a mass and by a spin. Now, a couple months ago, Hammer and Son wrote a paper that was entitled Unnuclear Physics. And they pointed out that unparticles can also arise in non-relativistic effective field theories. So what is a non-relativistic unparticle? Well, it's an irreducible representation of the Schrodinger group, which is the non-relativistic conformal group. It's the symmetry group of the Schrodinger equation for free particles. An unparticle is therefore characterized by a mass and by a scaling dimension. The Schrodinger group, it's the smallest group that includes a Galilean group and a phase transformation, and a scale transformation. In addition, you have to add one time inversion transformation for a total of 13 dimensions. So this is the non-relativistic conformal group. Hammer and Son also point out that low-energy neutrons are unparticles. I hope most of you know that a neutron is a bound state of 3 quarks, up, down, and down, with spin a half. But it's not so widely known that it can be described that low-energy neutrons can be described by a non-relativistic conformal effective field theory. It's the same effective field theory that you would use to describe ultra-cold fermionic atoms that are tuned to a Feshbach resonance that makes the scattering length infinitely large. If you have a single neutron, it is created by an operator with scaling dimension 3/2. This is the standard scaling dimension for a fermion or a boson in a non-relativistic effective field theory. If you have 2 neutrons, you might expect the operator that creates 2 neutrons to have scaling dimension 3, which is twice 3/2. But in fact, it has scaling dimension 2. And it's because of the interactions between neutrons that give almost infinite scattering length. If you go to 3 neutrons, at this point, you find scaling dimensions become non-integers. The scaling dimension for the operator that creates 3 neutrons is 4.27272. For 4 neutrons, the operator that creates them is not known so accurately, but it's roughly 5.1. And these are all quite a bit less than 4 times, these scaling dimensions are quite a bit less than n times the 3/2, the naive scaling dimension for weakly interacting systems. Now, I mentioned that low energy neutrons with opposite spins have this very large scattering length. Of course, if they have the same spins, they don't have S-wave scattering at all because of the Pauli principle. But they have an enormously large cross-section. And this is simply because there's an accidental fine-tuning in QCD that makes the dineutron almost bound. The radius of a neutron is roughly a little less than a Fermi, but the radius of the cross-section is more than an order of magnitude larger. And it's because these low-energy neutrons have such enormous scattering cross-sections that they can be described that the interactions are approximately scale invariant. The interactions would be almost the same if the cross-section was infinitely large. Now, Hammer and Son also pointed out how you might observe the unparticle nature. And That's if you have a nuclear reaction that in which two nuclei collide, a third nucleus is created, and also there are a number of neutrons produced essentially at a point through this interaction. These capital N neutrons will have the behavior of unparticle. You'll be able to study their energy distribution by looking at the invariant mass of this recoiling nucleus B. The recoil momentum. You'll be able to study the invariant mass of the neutrons through the real recoil momentum of the nucleus, and you find that the recoil momentum distribution will behave like a power law of the energy with a exponent that depends on how many neutrons. It's this power law behavior that is the signature for the unparticle.
Can I ask you a question about that?
Please.
So in the what I'm imagining, I don't know anything about nuclear physics, and I know that it's hard. But so I'm wondering, is this something which is proposed as a real observational probe, where people would actually measure these cross sections and hope to determine whether or not they're seeing this long range force, or is it? I guess the question will be, if I imagine setting this up, I have the effective theory that you're describing, where I kind of am idealizing. I'm not perturbing in this long range force, and so I'm thinking of these things as being, I can work to all orders, if you like, in the long range interaction. But the basic reaction that's dressing, how well understood is that? I mean, is it how do they know what the errors are in these powers?
Well, one correction is that it's really a short range force that's it's better to think of it as a short range force that's infinitely strong that gives this very large cross section. The neutrons have a small size, but they have a small size, but they interact strongly. If they have a small size, less than a Fermi, but they interact strongly if they come within less than about 10 Fermi. So it is a short range, a very strong short range force. But maybe the question, well, let me go to the next slide and see if it answers your question. So one example of such a nuclear reaction, although it's not all nuclei here, they gave an example of a pi minus hitting a triton, producing a photon plus 3 neutrons. And this is something that can be measured, and it has not been measured accurately, but it can be measured in the future. But this prediction of the unparticles is that there should be a scaling region in the energy at low energies where the cross-section scales like the energy to the 1.77 power. And this plot here shows the predictions of what is believed to be an accurate model for the low energy nuclear physics, and that's these dots that are going up on this line here. And the power law you see here is the 1.77. This power law is coming from final state interactions between those neutrons. And if you modify this model by eliminating the final state interactions, you would get a behavior with the energy that's the third power. So yes, they should experimentally be able to look at this reaction and see that the low energy behavior on the scale of a few MeV scales more like 1.77 than the third power that you'd expect from weakly interacting final state neutrons.
I guess my question is coming, I'm kind of visualizing, if I was to do this calculation, as being something like the distorted wave Born approximation, like if I was doing, the Coulomb effects in radioactive decays or something like that, keeping track of I'm working non-perturbatively in some interaction, which is strong. But it just seems like in order to pick out the scaling that's coming from the scatterings in the final state, I need to kind of also already know what the energy scaling was of the hard cross-section that I'm dressing. And how well are those things known? Like this E cubed expression, how accurately they know that it's really cubed rather than something else?
Well, the claim is really 1.77. The
But
E
there's
cubed, the E cubed is just the standard result of weak interactions. If you just work out the phase space for weakly interacting neutrons,
it's
you
just
find,
phase space.
yeah,
So the underlying cross section is not depending on energy in any interesting way. The hard process of the absorption of the pion and the
yeah. The assumption is that you set up a reaction where neutrons are essentially created at a point, and so you need the kinematics of this to be such that the photon is recoiling with a momentum much larger than the neutrons, and so they're all essentially produced at a point. So
okay.
arranging that they're produced at a point just comes from the kinematics of the reaction.
Okay, I think I've been thinking about it wrong. Okay, thanks.
Okay. What I wanted to point out is, and this is work with Hans Hammer that has been a follow-up of the paper with Damson, is that low energy neutral charm mesons are also unparticles. The simplest neutral charm mesons, for those of you who are not involved in heavy quark physics, are the D0, which is a spin zero bound state of UD bar with a mass of 1865 MeV, and the D star zero, which is a spin one bound state of UD bar with a mass of 2007 MeV. And there's a resonance that was discovered only early in 2003 that tells you that neutral charm mesons can in fact be described by non-relativistic conformal effective field theory. In this effective field theory, the charm mesons, they have the scaling dimension 3/2 that any fermion or boson in a non-relativistic field theory would have. If you have an operator that creates a pair of charm mesons, D star 0, D bar 0, or D0, D bar star 0, in the right channel, it'll have a scaling dimension of 2. If you have it in the opposite channel, if you in the channel with charge conjugation plus, it'll have scaling dimension of 2. In the channel with charge conjugation minus, the scaling dimension will be the naive scaling dimension that's twice 3/2, namely 3. If you look at operators that create 3 charm mesons, those that create XD0 will have a scaling dimension of 3.1012. Those that create XD0 star will have scaling dimension of 3.0870. So this will be a non-relativistic conformal effective field theory with non-trivial scaling dimensions. So what is this X3872?
Yes. Actually, before you leave that slide, so I didn't really understand why is the resonance telling you this?
Well, let me. Why don't you ask again in a couple slides?
Okay.
So let me tell you what this X3872 is. It was discovered at the E plus E minus collider by the Bell collaboration in 2003. It was discovered through the decays of the charge B meson into a charge kaon plus J psi pi pi, and there it turns out that there is a there was expected to be a J psi pi pi resonance coming from the psi 2s, the psi prime, but there was also an additional resonance that was at the energy 3872 that was completely unexpected. This most people believed, almost everyone believed, that the spectrum of charmonium, the bound states of a charm quark and anti-charm quark, were all pretty much understood by then. And suddenly, here in 2003, is a new state in the charmonium spectrum that was completely unexpected. It took 10 years, but the quantum numbers we eventually determined to be JPC is 1++, spin 1, charge conjugation plus. Its mass, back in the first discovery, was already seen to be surprisingly close to the threshold for D star 0, D bar 0. The most accurate measurements have been made recently by the LHCb collaboration, and their result is that the energy is probably below the threshold, by roughly 1/10 of an MeV, with an error bar of roughly 1/10 of an MeV, which translates into if it's below the threshold, the binding energy is less than 0.22 MeV at the 90% confidence level. The LECB collaboration also made the first measurement of the width, and if they assumed a Breit-Wigner line shape, they got a value for the width with an error bar. But this is not a good assumption for the line shape, because it doesn't take into account this nearby charm-meson pair threshold. And if you take that into account, you'll find the width is a lot smaller, perhaps a factor of 3 or 5 smaller than this measurement. So it has a very tiny, very narrow width. It's really extremely remarkable, much narrower than let's say the psi prime. It has 7 observed decay modes. It's you may be aware that there's a lot of new exotic heavy hadrons that have been discovered since 2003. This was the first one, but this is the one for which by far the most information is available. So what is the X3872? Well, we know its quantum numbers are 1++. Its binding energy is less than 0.22 MeV. And this tells you it has resonant interactions with neutral charm mesons. And these interactions will necessarily transform the X into a loosely bound molecule consisting of those charm mesons. Now, the wave function will has small additional components. The d star 0 can decay into d0 pi 0, so there'll be a long distance component, a 3-body component, d0, d bar 0, pi 0 with small amplitude. At short distances, there can be charged charm mesons, because 2 neutral charm mesons can scatter into 2 charged charm mesons. There may be a p-wave charmonium state. There may be a compact tetraquark state, but it really doesn't matter what the wave function at short distances. The fact that it has these resonant interactions with these neutral charm mesons will necessarily transform it into a state which is almost 100% loosely bound molecule consisting of d star 0, d bar 0. And it's a very large extended object. If you look at the binding and the lower bound on the binding energy, the upper bound on the binding energy, it tells you that the lower bound on the size of this particle is something like 5 Fermis. So it's an enormous hadron, enormously large compared to all other known hadrons. It's really a truly remarkable state. But this X, it is a bound state of the neutral charm mesons, and this arises because of an accidental fine-tuning of QCD that makes it just barely bound. And just like the neutrons have a large scattering length that comes from the fact that there's an accidental fine-tuning of QCD that makes the dineutron almost bound. In this case, this accidental fine-tuning makes the X just barely bound. And because of this, there will be these resonant interactions between the charm mesons, just like the resonant interactions between neutrons. Now, because of the existence of the bound state, if you look at the operator that creates the X unparticle, it is an operator with scaling dimension 2 instead of the naive 3. But this will not only create pairs of neutral charm mesons, d star 0, d bar 0, and d0, d bar star 0, but it also create the X. And if you look at the XD unparticle, the operator that creates this, has a scaling dimension of 3.1012. It will create 3 neutral charm mesons, but also a bound state plus 1 charm meson. Similarly, the XD star unparticle with scaling dimension 3.0870 will create not only 3 charm meson states, but also the bound state plus 1 charm meson. Now, yes,
this is
please.
Is the small difference between the 2 scaling dimensions due to the difference between the masses?
Yes,
D and D star?
Yes, that's all it is. It's just the difference between 1865 and 2007.
Mm-hmm.
Okay, well, I claim that the unparticle actually has been observed. The Babar collaboration in 2019, they put out a paper in which they looked at inclusive decays of the charged B meson into a charged kaon plus anything, and they measured the momentum distribution of the K plus minus, and this momentum distribution contains the information about the energy distribution of what is recoiling against it. And this is their data. And if you look at this carefully, you'll see that there's a blue curve that runs through a lot of the data. This blue curve has the effects of all the known charmonium states that would contribute to this. There's the eta C and the J psi and the chi C0 and the chi C1 and the chi C2 and the eta C prime and the psi prime, and maybe even a hint of the psi double prime. And this, including these, gives a very good fit, except in this region near 3872. And so there is a peak in this region of 3872 that is not predicted by the known charmonium states. Given the energy 3872, the peak is, by kinematics should be at 1141 MeV. And I would interpret this as an actual observation of the unparticle. This peak in the momentum distribution is telling you about this unparticle. However, to really make this convincing, what you need to see to let's say confirm that it is the unparticle, is to see a scaling region near this momentum that with the scaling region with momentum determined by the power law of this unparticle operator, which is 2. So you need to be able to see on the low side of this peak the behavior P max minus P to the -1/2 power. And if you could see that, then that would confirm that what you are seeing is the X unparticle. Now, the data that was used by Babar collaboration was that collected in previous decades. And there's a new experiment by the Bell 2 collaboration in Japan that will accumulate that should accumulate about 40 times the statistics of the previous B factories. And my hope is that the Bell collaboration might be able to see the scaling behavior near P max is 1141. That would be the smoking gun for the unparticle nature of this peak.
Hey, Rick,
yes.
Can I ask you a question? So does this graph then tells me that the X3872 could be a weakly bound charm meson molecule and also an unparticle? Is this what your conclusion is? I mean,
no, it's the fact that its binding energy is so tiny, it's so close to the neutral charm meson threshold, it is necessarily a large extended object that's a bound state of 2 neutral charm mesons. So okay. No, it's very definitely that. But in order to, it'd be nice to see to verify quantitatively the predicted momentum dependence of the unparticle, okay, which is captured in this scaling behavior of with power -1/2.
Okay. Thanks.
Okay, what about the XD and XD star unparticles? Well, to produce an XD or XD star unparticle, you need to create 2 CC bar pairs because the X contains a C and a C bar and the D contains a C. So you'll need to create 2 CC bar pairs. And the only way to get that at a sufficient rate is from prompt production at the Large Hadron Collider. Now, if you go to LHC, there's no trigger for events with 3 charm mesons. There'll be enormous amount of data. The enormous number of events with 3 charm mesons. Many of them 3 charm mesons created at a point, but you won't be able to. There's no trigger that will be able to see the 3 charm meson component of an unparticle. What you need is the X. The X decays into J psi pi pi. The J psi decays into mu plus mu minus, and this provides a trigger. So you collect J psi events And then from those, you identify the X events. And then within those, you'd look for an additional D0 or D star 0. And so the XD unparticle could be observed through the X plus D0 component of the unparticle. There should be a scaling region with energy dependence, energy of the minus 0.1012. Their XD star unparticle could be observed through the X plus D star 0 component. And in this case, there'd be a scaling region with energy dependence that's essentially indistinguishable. It's either minus 0.0870. These scaling dimensions, I'm a little proud of it, the way these numbers were obtained. First, Hans Hammer did some calculations that gave us the scaling behavior to a couple digits. But then I was able to take some 3-point functions from the ADS CFT correspondence, do a Fourier transform into momentum space, and then amputate them. And from those, we were able to get a simple analytic expression for these energy dependencies. Anyway, if one could see this energy dependence, it would be, well, this would be the smoking gun for the XD and XD star unparticles. And it's possible they could be observed by the LHCb collaboration, especially when the high, well, there is a chance they can be observed by the LHCb collaboration. Okay, so that's all I really wanted to tell you. Let me just summarize that a non-relativistic unparticle is an excitation created by an operator with definite scaling dimension in a non-relativistic effective field theory. Low energy neutrons are unparticles because the dineutron is almost bound, as pointed out by Hammer and Son. Low energy neutral charm mesons are unparticles because of the existence of the X3872 resonance that is just barely bound. The X unparticle has perhaps been observed already in inclusive decays of the B mesons. The XD and XD star unparticles might be observable through prompt production at the LHC. And finally, a question I would like to ask is whether unparticles can be observed using ultra-cold atoms. And I haven't thought of a way that this could be done yet, but that would be an interesting thing to understand. So thank you very much for your attention.
Thank you. That's as you said, it's a new record for how prompt our speakers have been. so we shall open the floor to any questions. Go ahead,
I did have a question.
Yeah.
Yes. Oops. Mm-hmm.
Ask question first. Yeah. So can you explain this delta and these exponents of E minus 0.1? Because I remember in the paper that we wrote with Hans, the power is delta, the dimension minus 2.5.
Mm-hmm. Yeah, so let me go back. Let me try to share the screen with a iPad. Okay, hang on a second. It's trying to connect. Okay, so well, that power is something like that power delta. Okay, so it was, once again, it was, well, minus 0.1. And it turned out to be just delta 3 minus 3, I think. But the way we got this was to, the way that we got the accurate result was to start with the expressions for the 3-point function of the or for the 3-point function in coordinate space that's obtained from the ADS-CFT correspondence, and then Fourier transform into momentum space, and then amputate the final states, and this will give you the result for creating a 3-point function. Sorry, creating creating the three unparticle operator point and producing the two particle point creation of the three unparticle, producing a 2 unparticle and a single particle. And what we found is that if this is energy 3 coming in, if these are on shell, these are with momentum plus p and minus p. And you'll find that this scales like energy to the something like minus delta 3 plus delta 2 minus delta 1 over 2. And this, if you take this amplitude and square it and integrate over space to get the rate, you'll get E3 to the delta 3 minus 3, I think. Delta 3 is this number that's 3.1 or something. And so this is 3.1. The delta 2 is 2, and the delta 1 is, 3/2. And this is what gave me the minus 0.1.
I thought it's, my question is maybe it's more trivial. It's, should it be plus 0.1?
Okay, the answer better be no, otherwise I screwed up badly. Sorry, I have these wrong. This is energy to the power minus delta 1 plus delta 2 minus delta 3 over 2. And I'm hoping that gives me the right answer. So this was 3 point something small. This was, sorry, can I erase? Let's see. Okay, so this is 3/2 plus 2 minus 3.2 or something like that. Let me just verify. Yeah, 3.1. 3.1. Five halves. So this looks like e to the 0.3/2. So minus 0.4. Anyway, sorry. Okay, I think minus 0.2. And then I have to square it and add a half from phase space or something. But anyway,
Okay.
I'll certainly check if I got the sign wrong, but I hope not.
So it's not just this delta. Oh, okay. Thank you.
There was a question also from Fayez. I don't know if he's still here. Maybe.
Is this in the chat or something?
No, he actually had spoken up when Son first came in, and so but he might have been answered. Why don't we? There's a question here from Wei Sui. So why don't we go there? So go ahead, ask your question.
May I ask a basic question? So
Sure.
when you mentioned the 1-2 neutron scattering, the cross section is large, and why you conclude that this is conformal? And I possibly missed one step. And how do you get delta equal to 2? And
Okay, so let me go back to. So let me go to try going back to the slides if that's okay. So
yeah.
share. Okay, so if you were able to tune either the up quark mass or the down quark mass or alpha S, the parameters of QCD, you could arrange that the dineutron be just barely bound, or you could arrange that it would be the binding energy be 0. In that case, the interactions, the range, well, this cross section would be infinitely large. This radius would be infinitely large, and so there's no dimensional parameters that describe the interaction. You have interactions that are described by no interaction with no dimensionful parameters, and that's exactly what you need for conformal symmetry, for a non-trivial conformal symmetry.
Should I think this is really strongly bounded, or is that why I think that not strongly bounded? Should I really think it's strongly interacting, or is it like weakly interacting?
No, it's very strongly interacting.
It's very strong. I see.
If I don't know if you know anything about ultra cold atoms, but in the last couple of decades, one of the main themes of ultra cold atom physics was studying the case of strongly interacting atoms, where they would tune a magnetic field to get a bound state exactly at the threshold for the two atoms, and this would produce two atoms with infinitely strong interactions. They could also tune this magnetic field to a case where the interactions are 0 because of a cancellation, and you could study extremely weakly interacting atoms. But no, when you tune a bound state exactly to the threshold, you have extremely strongly acting interactions, as strong as allowed by quantum mechanics.
Mm-hmm. Thank you. Then how do you get delta equal to 2? Just naively, and is it easy to see this?
I'm sorry, can you repeat this?
How do you get delta 2 equal to 2, like the power counting?
Well, okay. Let me try going back to the iPad if you don't mind. Sorry, share screen, iPad, share. I have to do screen mirroring again. But okay, so I can show you diagrammatically how you would go about it. Yeah, so if you have just point like S-wave interactions, it would give you a interaction like this. But if you tune to the strong interacting point, you should calculate the cross section by summing all these diagrams to all orders.
Mm-hmm.
And if you do that, well, when you do this integral will involve some ultraviolet cutoff, and some kind of renormalization will be necessary. But if you do this, you'll find that this geometric series sums up to something of the form -1/a plus square root of 2 mu e or something. And if you tune this, so this is a finite parameter after renormalization, you can tune it to 0. And in that case, what you'd get is minus 2 mu e to the minus 1/2 power. And okay, so you're asking why is it delta equal 2? Sorry, why does this tell me that delta is 2? Okay. If you look at the 2-point function in momentum space, this is a scattering amplitude, but I could have done the same thing for the 2-point function, and I would find that it behaves like the energy to the power delta minus 5/2, and it's setting minus 1/2. Yes, so come on. Delta minus 5/2, setting this equal to minus 1/2 tells me that the scaling dimension is 2.
Yes, thank you.
There's also a question in the chat. I don't know if you can see that, Eric.
I don't think I can see the chat while I stop.
Let me read. I can read it to you if you like.
I can read it myself. Yeah, go ahead, read it, but I'll read it as well in parallel. Go ahead, read it.
Okay, it says the X 3872 is visible in heavy ion collisions, and there's a link to a CMS paper there. A distance of 5 Fermis is certainly filled with other hadrons and energy. Such a large state as X does not make sense, so we must be seeing the short distance component that you say is not relevant. Is that right?
I'd say no, but it's an open question. But this paper that's being referred to here is really a marvelous result. The X decays into J psi pi pi, and the psi prime also decays into J psi pi pi. So a very good benchmark for studying any reaction involving the X is to compare it to the corresponding reaction involving psi prime. And if you look at B meson decays, if you look at prompt production at the LHC, you find that the X signal is an order of magnitude smaller than the psi prime signal. So it's a very definite resonance, but still it's order of magnitude smaller than the ordinary charmonium state. The psi prime, what is it, 3686 or something? It's not so far from 3872. But in heavy ion, CMS found that in lead-lead collisions, they found that the production rate of X is comparable to that of psi prime. So there's the relative rate of X and psi prime is increased by an order of magnitude in heavy ion collisions. And so that's a really amazing result that calls out for an explanation. So let me, okay, so let me read the end of the question again. A distance of 5 Fermis, which is my claim is that the X must have a size larger than 5 Fermis, is certainly filled with other hadrons and energy, such large state, does not make sense. Okay, so yes, if you have heavy ion collisions that are producing the quark-gluon plasma or whatever, all the particles are, there's lots of particles within a distance of 5 Fermis. And so the X, it does not make sense to have the X produced in that phase. My hope or my belief is that the X is actually produced it's actually produced when there's the freeze out. At some point, the quark-gluon plasma expands, and there's a transition to a hadron gas. And somewhere in the expansion of the hadron gas is where I believe that the X would actually be produced. And the challenge is to show that it's produced in order of magnitude more strongly than the psi prime. So that's my that's my belief. No one has shown that it's plausible, but the question is right that the X, a 5 Fermi object, cannot survive in a dense medium where there's lots of particles within 1 Fermi. But so I believe that the X is produced at in the freeze out stage of these heavy ion collisions, but I've not shown that it's plausible yet.